Welcome! Today we're diving into a fascinating phenomenon, how tiny contact areas at the nanoscale can produce surprisingly strong adhesion forces. This explains why supposedly non-sticky materials can actually stick very hard at small scales. Let's start with a puzzling observation. You might think materials like silicon or glass are non-sticky, but at the nanoscale, they exhibit remarkable adhesion. Why is this? The key is understanding the difference between apparent contact area and real contact area. When you look at a surface with your eyes, you see the apparent area. But at the nanoscale, only tiny asperities actually touch. Imagine two rough surfaces coming together. The apparent contact area is large, but the real contact happens only at a few nanoscale asperities. These tiny contact points are where adhesion concentrates. Here's a critical question. Why does concentrating contact into tiny areas actually increase adhesion per unit area? Shouldn't it be the same regardless? The answer involves surface energy. At macroscopic scales, bulk mechanical properties dominate, but at the nanoscale, surface forces become extremely important relative to volume. Two fundamental models describe nanoscale adhesion, the JKR model and the DMT model. Both consider elastic deformation and surface energy, but they apply to different material properties. The JKR model, developed by Johnson, Kendall, and Roberts, applies to relatively compliant materials with high surface energy. Think of soft elastomers or biological materials. The DMT model, by Derjaguin, Muller, and Toporov, applies to stiffer materials with lower surface energy. This includes many ceramics and hard polymers. The JKR adhesion force is 3/2 pi RW, where R is the radius of curvature and W is the work of adhesion. This is the pull-off force needed to separate two contacting bodies. The work of adhesion W equals gamma 1 plus gamma 2 minus gamma 12, where the gammas are surface energies of the two materials and their interface. Let's look at a real-world example that frustrated many researchers. Atomic force microscope tips unintentionally picking up nanoparticles. When an AFM tip approaches a nanoparticle to measure it, the tip often picks up the particle instead. This happens because the adhesion force is surprisingly large at this scale. Let's do a numerical estimate. A typical sharp AFM tip has a radius of curvature of about 10 nanometers at the apex. For silicon and air, the work of adhesion is roughly 0.1 joules per square meter. This accounts for van der Waals forces and any adsorbed water layers. Plugging into the JKR formula, F equals 3/2 pi times 10 nanometers times 0.1 joules per square meter. This gives us approximately 4.7 nanonewtons. That might sound tiny, but let's compare it to the particle's weight. Consider a silica nanoparticle with diameter 100 nanometers. Its mass equals density times volume. Silica density is about 2,200 kilograms per cubic meter, and the volume is 4/3 pi r cubed. This gives a mass of about 1.15 times 10 to the minus 18 kilograms. The gravitational force is mass times g, which is about 1.1 times 10 to the minus 17 newtons. Notice that the adhesion force is about 400 times larger than the weight. So the adhesion force completely dominates over gravity. This is why the particle sticks to the tip rather than falling off. Now let's explore a beautiful natural example, the gecko's foot. Geckos can climb vertical walls and even hang upside down from ceilings. How do they do it? A gecko's toe pad contains millions of tiny hair-like structures called setae. Each seta branches into hundreds of even smaller structures called spatulae. These spatulae are only about 200 nanometers wide. Each individual spatula adheres using van der Waals forces, which are very weak. But here's the genius. By splitting the contact into billions of tiny points, the gecko achieves enormous total adhesion. This raises an important question. Why is it better to have many small contacts rather than one large contact with the same total area? The answer has two parts. First, having many small, flexible contacts ensures that more of them actually make contact despite surface roughness. Second, it distributes stress more evenly, preventing crack propagation. The total force is the number of contacts times the force per contact. If we have n contacts, each contributing F single, we get n times F single total. A gecko foot has roughly 2 billion spatulae. Let's estimate the adhesion. Each spatula can exert about 10 nanonewtons of force. This has been measured experimentally. Multiplying 2 billion times 10 nanonewtons equals 20 newtons per foot. With 4 feet, that's 80 newtons total, enough to support a typical gecko weighing about 50 grams many times over. In fact, the gecko typically uses only a small fraction of its adhesive capacity, giving it a large safety factor. The principle of contact splitting is now being applied in synthetic adhesives. By mimicking the gecko's hierarchical structure, engineers create materials with controllable adhesion. Compare a single large contact patch to many small ones. The split contacts conform better to rough surfaces and resist peeling more effectively. Whether JKR or DMT applies depends on the Tabor parameter, which characterizes the balance between elastic and adhesive forces. The Tabor parameter μT equals RW squared over E star squared times Z0 cubed, all to the 1/3 power. Here, E star is the reduced modulus, and Z0 is the equilibrium separation. When μT is greater than about 5, the JKR model applies. This means compliant materials with large contact areas. When μT is less than about 0.1, the DMT model applies. This means stiff materials with small contact regions. Let's examine what happens during contact at the nanoscale more carefully. When a sphere contacts a flat surface under load, it deforms elastically. In the JKR regime, attractive forces act inside the contact zone, pulling the surfaces together and increasing the contact area beyond what pure mechanics would predict. The JKR contact radius A cubed equals R over K times the quantity P plus 3 pi WR plus the square root of 6 pi WR P plus 3 pi WR squared. This shows how adhesion increases contact area. Notice something remarkable. Even when P equals 0, there's still a finite contact area due to adhesion. This is purely due to surface forces. Understanding nanoscale adhesion has profound implications across many fields. In microelectromechanical systems, stiction or static friction due to adhesion is a major failure mode. Tiny moving parts stick together permanently. In nanomanufacturing, controlling whether nanoparticles stick or don't stick is crucial for assembly and patterning. In biology, cells use nanoscale adhesion complexes to sense their environment and generate forces. Understanding these forces is key to tissue engineering. Let's calculate adhesion for a MEMS cantilever beam that might stick to the substrate. Imagine a silicon cantilever 10 micrometers long and 2 micrometers wide, suspended 100 nanometers above a substrate. The adhesion force is approximately AW over D, where A is the area, W is work of adhesion, and D is the separation distance. Plugging in, area is 20 square micrometers, W is 0.1 joules per square meter, and separation is 100 nanometers. This gives about 20 micronewtons of adhesion force. The elastic restoring force of the cantilever is K delta, where K is the spring constant. For a beam, K equals EWT cubed over 4L cubed. If the adhesion force exceeds the maximum restoring force the cantilever can generate, it will collapse and stick to the substrate permanently. This is a critical design consideration. How do engineers combat unwanted nanoscale adhesion? One approach is coating surfaces with low surface energy materials like fluoropolymers. This reduces the work of adhesion W. Increasing surface roughness reduces real contact area. However, this must be controlled carefully, as too much roughness can increase adhesion by creating many small contacts. Using stiffer materials reduces the contact area under a given load, following the Hertzian contact mechanics. Let's return to our original paradox. Why do non-sticky materials stick at the nanoscale? At the macroscale, even seemingly smooth surfaces are rough. The real contact area is a tiny fraction of the apparent area, so adhesion forces are diluted. At the nanoscale, surfaces can be molecularly smooth over the contact region. The entire apparent area becomes real contact area, and stress concentrates. Adhesion stress equals force divided by real contact area. At the nanoscale, A real approaches A apparent, so stress becomes very high. Additionally, surface energy scales with area, while volume and weight scale with size cubed, so surface effects dominate at small scales. There's another important contribution to nanoscale adhesion: capillary forces from adsorbed water. In ambient conditions, surfaces are covered with a thin layer of adsorbed water. When two surfaces come close, water bridges form between them, creating minutiae. The capillary force equals 4 pi r gamma cosine theta, where gamma is surface tension of water and theta is the contact angle. For a 10 nanometer radius tip with water, this gives about 9 nanonewtons, comparable to the van der Waals adhesion. This explains why adhesion measurements are very different in vacuum versus ambient air. Removing the water layer dramatically reduces adhesion. The Gecko's adhesive is remarkable because it's reversible and controllable. How can we achieve this in synthetic materials? One strategy is creating angled pillars that adhere strongly when loaded normally but peel easily when sheared in one direction. Hierarchical branching, like the Gecko's setae and spatulae, provides compliance at multiple length scales, ensuring good contact even on rough surfaces. High aspect ratio pillars can bear large shear loads but buckle and detach easily under normal pull-off, giving directional adhesion. Let's summarize the key physics principles we've covered. At all scales, real contact area is smaller than apparent area due to roughness, but at the nanoscale, this difference becomes minimal for smooth surfaces. Surface energy contributions scale with area, so they dominate over volume-dependent properties at small scales. The JKR model applies to soft, high surface energy contacts. The DMT model applies to stiff, low surface energy contacts. The Tabor parameter determines which regime you're in. By dividing a contact into many small subcontacts, like the Gecko does, you maximize real contact area and distribute stress, achieving strong yet controllable adhesion. Understanding nanoscale adhesion is crucial for designing MEMS devices, manipulating nanoparticles, developing synthetic adhesives, and understanding biological systems. The take-home message is profound. At the nanoscale, adhesion is not just important, it's dominant. Any device or process at the micro or nanoscale must account for adhesion forces or risk catastrophic failure from stiction or unwanted particle pickup. Nature has evolved elegant solutions, like the Gecko's foot, that use hierarchy and contact splitting to achieve remarkable adhesive performance. By understanding and mimicking these principles, we can design new materials with tunable, reversible adhesion for applications from climbing robots to medical bandages.